Welcome to the video for Chapter 31. Today we're going to talk about characterizing antennas, the ways in which we can identify the parameters that will describe an antenna and how we can use those parameters to perform very useful calculations. We'll talk about input impedance, we'll talk about half power beam width, directivity, gain, effective area, and then we'll see how we can bring all of that together using what we call the Freeze equation. So our historical perspective today is Edwin Hubble. You probably heard of the Hubble Space Telescope. Hubble was actually the first person to discover galaxies outside the Milky Way, and then he also used the information that he gained from that study to determine that those galaxies were redshifted, and that helped him to realize that the universe was expanding. He was actually probably the most important astronomer of the 20th century. So we're happy that he was able to use radio telescopes, or basically large antennas, to be able to perform that work. So let's talk a little bit about input impedance. We've spent a lot of time this semester talking about how to match the impedance of a transmission line to the impedance of the load. We tended to think of the load as something that we were given that couldn't be adjusted, but now we begin to see that the antennas that we're working with are the loads of many transmission lines. So we need to be able to understand what is the input impedance of an antenna. And up until now, we haven't really addressed this in any way, so we need to understand how can we calculate that input impedance. So we have here a figure that shows how an antenna is serving as the load. You can see here, this over here is actually the antenna, and we're sending it a, oh, that shouldn't say cosine of, that should just say cosine right there. We are sending it a sinusoidal signal, and it's going to have a frequency of omega and a wave number of k, and the length of the transmission line is L. So if we draw a sphere around the antenna, so whatever this antenna is, so let's imagine that we've got a dipole antenna that's over here. I'm going to draw a sphere around the dipole antenna, and I'm going to figure out what is the total radiated power. Now, we actually did calculate the total radiated power for an infinitesimal dipole antenna. We haven't done it for a finite dipole yet, but we did do it for an infinitesimal dipole, and it wasn't super hard for the infinitesimal dipole. We can now use whatever the amount of power is that is intersecting with that sphere. So if we calculate the total radiated power that is intersecting with that sphere, and if we assume that the antenna has no losses inside of the wires, which is a reasonable but not perfect assumption, then we can say that all of the power that is going in to the antenna must be converted into radiation, and that radiation will necessarily have to intersect the sphere. So we can say that the radiated power is equal to I RMS squared times the input impedance. Or just I sub 0 squared over 2 times the input impedance. And we can then rearrange that to calculate the input impedance, or the input resistance of an antenna, is going to be 2 times the radiated power divided by I sub 0 squared. Now, we can do this for an infinitesimal dipole because we have already seen the total radiated power of an infinitesimal dipole from Chapter 29. We have an equation for the radiated power. So we're going to plug that into equation 31.2. We're going to do a little bit of algebra on that equation, and ultimately we can solve for Rn, and Rn turns out to be 80 pi squared times L over lambda, the quantity squared. So we have an expression that allows us to calculate the input impedance of an infinitesimal dipole antenna. It's not at all clear to us what sort of range of numbers we're going to be talking about. Is it ohms? Is it kiloohms? Is it mega ohms? So let's do a quick example. We want to know what is the input impedance of an antenna that is 1% of the wavelength of the signal. How much current would then have to be provided to this antenna in order to radiate a total of 1 watt of power? 1 watt is not very much, so we're talking about a relatively small amount of power that we would be radiating. We want to know how much current would that require. Well, we know that we can calculate Rn is equal to 80 pi squared times 0.01 lambda divided by lambda, the quantity squared. The lambdas, of course, are going to cancel, and we're left with 0.0789 ohms. Now, if that number seems ridiculously small to you, good job. It is ridiculously small. What we're going to find is that the infinitesimal dipole antenna offers resistances that are so small that it's practically impossible for us to use it as a realistic antenna. I've mentioned to you a couple of times now that the infinitesimal dipole is just not going to work properly as a realistic antenna, that the finite dipole is a much better choice. Today is the day that we find out why, and really this is the #1 reason why. It is really hard to push any significant amount of power into a resistor that's 0.0789 ohms. It would be like trying to throw a Kleenex. You know, you can put as much energy into it, as much power into it as you want. You're not going to throw that Kleenex very far. Similarly, if the resistance were super high, then we wouldn't be able to put very much energy into it, and that would be like trying to throw a car. In between is like trying to throw a football or a baseball. That's the sweet spot where you have something that's just about the right size. So in the same way, we're going to find that there are resistances that are just about the right size, typically on the order of a few tens of ohms, maybe 100 ohms would be a really good amount of resistance for an antenna, but 0.0789 is just not going to do it. We were also asked to calculate if we wanted 1 watt of power, how much current would we have to send to this resistor. So the power is 1/2 I squared times R. And so I, which is the amplitude, I probably should call that I sub 0. I sub 0 is equal to 2P divided by R, and then take the square root of that. So this is 2 times 1 watt divided by 0.0789. Take the square root of that, and I get 5.03 amps. 5 amps. You'd have to deliver 5 amps to this antenna to get 1 watt out of it. Now, if you think 5 amps seems like a lot, yeah, it is. Now, antennas take 5 amps all the time. That's not a problem, but they should be able to deliver a lot of power for 5 amps. This one's delivering 1 watt of power. It would be like if your cell phone were using 5 amps to drive the antenna. That's just not going to work. So we have a plot of what the input impedance for an infinitesimal dipole looks like. And notice here that like this is the point that we just were working with, 0.01 lambda. And you can see that, yes, it is a very tiny fraction of 1 ohm. Now, if we get up to a tenth, so if we have 10%, then now we're up into the 7.5 ohms, 8 ohms in that range. That's still not great, but it's significantly better. But just remember that the true definition of an infinitesimal dipole is that L has to be less than lambda over 50. So really, the definition of an infinitesimal dipole ends right there. So you can see for all of that range, it's less than 1/2 ohm. Now, we can also calculate the input impedance of a small loop antenna, and I've just sort of listed it here for you. Remember that A is the radius of the loop. And so the small loop antenna has a behavior that's similar to the infinitesimal dipole. It's also going to be a very low resistance, and so that can be problematic. Now, calculating the input impedance of a finite dipole is much more challenging. It requires integrating the average Poynting vector. And I don't know if you remember what the average Poynting vector looks like for a finite dipole, but it's from chapter 30, and this is what it looks like. As you can imagine, this has, remember that function that is the cosine of a cosine? I don't even know how to integrate that. There are mathematicians who have figured out how to integrate it, and I'm just going to tell you that we're going to use the result of their integration here. This is what the input impedance looks like. This is one large equation, and I had to spread it across 3 lines, and even this has to use some notation that we haven't seen before. This C right here appears here, and I think it also appears here. We also have introduced C sub I, so C sub I is a function, so C sub I appears there, and then C sub I appears there, and then C sub I appears there. That's what's known as the cosine integral. The cosine integral is actually a well-known function. It doesn't appear very much in electrical engineering or computer engineering, but it does appear here. And then we also have S sub I, which appears in 2 different places. S sub I, as you might guess, is the sine integral. And so the sine integral, the cosine integral and the sine integral are well-known functions, so well-known, in fact, that they actually appear in MATLAB as commands. You have cosint and sineint. And you can evaluate whatever value of x you want it to be. You can plug that in. And so what I did was I took the full equation for the input impedance of the finite dipole antenna, this equation 31.8, and I wrote a MATLAB code to plot it. And this is the plot that I get. So I'm going to talk about this figure for some time because this is the most important figure in this entire course. You could, of course, using the equation 31.8, you could figure out what is precisely the input impedance of any length of finite dipole, but it's a real hassle. And so my advice to you for this class, and to a certain degree as a professional engineer, this is one of the things you can look up in a table. Most of the time, civil engineers look up in things in a table and electrical and computer engineers don't. This is one place where you definitely can. So I think that this graph, which is a pretty complicated graph, you got this oscillation thing going on, but it still has an upward slope. One thing to notice about this graph is that everything that was on figure 31.2 can be contained within this portion of the graph here. So all of that previous figure for the infinitesimal dipole is all in the first segment of this figure. And so it looks as though in this figure, it looks as though it's actually just straight flat there. But if you go back to figure 31.2, you can see that it actually is starting to ramp up, but it doesn't really start to ramp up until you get up to maybe, let's say, in the neighborhood of 0.5, or certainly by the time you get up to 0.9, you've hit actually a local maximum. Those are good solid antennas. These are places where if you look over here on the horizontal axis, the half-wave dipole is going to have somewhere in the neighborhood of 70 to 75, maybe 80 ohms of input resistance. At this local peak here, it's somewhere in the neighborhood of 210 ohms. So if I said to you, here is the length of an antenna, you can notice that I've added finer grid marks here, so you can look it up pretty precisely. If I said, you have an antenna that is 1.5 times lambda. So you could come over here to 1.5, you could come over here and say that's going to be right at 100 ohms of input impedance. That's much faster than using the equation that appears on the previous page. So at least for our purposes in this class, I will encourage you to use this graph, and certainly in an exam or in the final exam setting, this is the graph that you should use. So now we're talking about things that are in the neighborhood of tens to hundreds of ohms. This is in our sweet spot. This is where we can put some power into it and get some power out of it. So let's do example 31.2. What is the input impedance of a half wavelength antenna? So a half wavelength dipole antenna. I kind of already did this one for you, but let's do it more precisely. That's the point where it crosses where the blue line crosses the 0.5 wavelength line. And if I come over here, that's somewhere in this, probably in the 70 to 75 ohms. So 70 to 75 ohms. And I actually did do the math for you, and I found out that 73 ohms is the precise answer. And so 73 ohms is the input impedance, which is also, by the way, called the radiation resistance of a half-wave dipole antenna. And that's a pretty good number to know, because as I mentioned a couple of times, half-wavelength antennas are very commonly used. You're using a transmission line with a characteristic impedance of 100 ohms to transmit a signal with a wavelength of 3 meters. What is the shortest antenna that would be impedance matched with this line? So we know that we need the input impedance of the antenna to be 100 ohms. So what I'm going to do is basically I'm just going to go across here, and at that horizontal line of 100 ohms, anywhere that I cross that line, that's going to be an impedance matched antenna. But it did ask for the shortest antenna that would do that, and so that's going to be right in this neighborhood here. So if I come down here, that's going to be, about 0.55 lambda. So I'm going to see that L is equal to 0.55 lambda, but we were given lambda as 3 meters. So this is 0.55 times 3 meters, which is 1.65 meters. So right away you can see that we have a lot of new capabilities here. We can figure out how to adjust the antenna to match the impedance of the line that we're given. Now, of course, we need to be careful because that can also depend on the wavelength. So if this wavelength lambda changes, then we're going to end up with a different length of antenna. And of course, we know that any signal that we're actually transmitting is actually going to be over a range of frequencies, and so therefore it's going to be over a range of lambdas. So all we can do is maybe pick the middle value and hope that it's not too wide, maybe design it so that it's not too wide, and then hopefully that entire signal, that entire range of lambda will fall within a reasonably matched value of the impedance. Okay, so let's talk a little bit about directivity. As I've mentioned to you a couple of times before, directivity, which is also known, by the way, as directive gain. It turns out that in this chapter, there's lots of different terminology for the same idea. So we had input impedance, which I also called radiation resistance. We have directivity, which is also known as directive gain. Directivity measures the degree to which the radiation emitted by an antenna is concentrated in a single direction. Now, there are times when you would like to have a very directed antenna. You know, if you imagine that you're trying to figure out, hey, where is this airplane? Maybe you're working for the air traffic control, or maybe you're working for some sort of a defense system. You have some sort of an antenna down here, and you want to send a beam out to detect where that airplane is. And then as the radar is reflected back, then you'll know where the airplane was. Now, if you have a nice narrow beam, as I've shown here, then you can really localize that airplane. But let's imagine if the beam were more like this. Then all I could say is, oh, it's somewhere in that beam. The wider the beam, the less knowledge we have about the location of that airplane. The narrower the beam, the more certain we are about the location of that airplane. So that's a good example of a place where you would definitely want to know that you could get the narrowest beam that was reasonable. But if you were thinking, oh, I'm going to work for a radio station, I'm going to work for a TV station, in those cases, you don't want to just beam your signal to one neighborhood. You want to send it to the whole city. So there we'd like to have an antenna that is going to be transmitted equally in all directions. By the way, that means that's an isotropic antenna. So if you hear the word isotropic, iso means same and tropic means direction. So isotropic means it's the same in all directions. For example, you can have the case where you'd like to have a narrow antenna, or you can have the case where you'd like to have a broad antenna. So just be aware that when I'm talking about directivity, it's not always desirable to have a high amount of directivity, but in those cases where you do need a high level of directivity, we need to be able to figure out how to do that. So the directivity is defined mathematically as the ratio of the maximum radiation intensity that an antenna creates in a particular direction divided by the average radiation intensity over all directions. You know, it's sort of like, imagine if you are very good at one thing. If you are like, if you are the badminton champion of the world, but in everything else you're completely incompetent, well, then you're very directed. You have a very high level of directivity. Or if you're just a good athlete who's good at almost everything, and then therefore you're also pretty good at badminton, then you wouldn't be as directed. You'd be much more like an isotropic antenna. So here we're thinking about, you're taking the maximum value divided by the average value. And the average value is just the total radiated power divided by whatever area it is, like the area of a sphere that you would be typically doing the integration of that radiated power over. So typically we'll take this area and we'll move it up into the numerator, because if it's in the denominator of the denominator, you put it in the numerator. So that's why this A appeared right here. The radiated power, of course, is just going to be this is typically the Poynting vector. So the intensity I is the Poynting vector. This r squared sine theta d phi, that's the surface area in spherical coordinates in the r direction. And so if you think about what is the sphere that we're working with, well, it's in the a sub r direction. So we want r squared sine theta d phi. So if you can do this integral in the denominator, then you can calculate the directivity of an antenna with perfect precision. That integral can be very challenging sometimes, but we can in fact do it for the infinitesimal dipole. So let's take a moment and do the infinitesimal dipole. We know that the average Poynting vector for an infinitesimal dipole is 1/2 z sub 0 times k sub 0, or just k, sorry, it's just k, times I sub 0 times L, that quantity squared, divided by 16 pi squared, and that line should be shorter, and then 1 over r squared sine squared theta, and it's in the a sub r direction. We can also say the radiated power, which we actually found in the lesson where we introduced the infinitesimal dipole, is equal to z sub 0 times k I sub 0 L, the quantity squared, divided by 12 pi. And we can say, what is the maximum value of the Poynting vector? S sub AV comma max. Well, the only thing that varies in here with theta is the sine squared theta. And the maximum value that sine of theta can take on is 1. So I'm going to leave everything else the same, 1/2 z sub 0, I have a k, I sub 0, L, the quantity squared over 16 pi squared 1 over r squared times 1. So that's the maximum value that S av can take on, and that's still in the a sub r direction. So now what I want to do is I want to figure out the directivity. The directivity is going to be the surface area. It's the surface area of a sphere, 4 pi r squared, times the maximum value of the intensity. So this is 1/2 z sub 0 times k sub k. I did it again. Just k times I sub 0 times L divided by 16 pi squared. That quantity squared. Whoops. Oh, darn it. Only the numerator gets squared. So this is k I sub 0 L, the quantity squared over 16 pi squared. And then there's also a 1 over r squared. And then in the denominator, we take the total radiated power, which is this quantity right here, that goes down to the denominator, z sub 0 times k I sub 0 L, the quantity squared, over 12 pi. Okay, a lot of canceling. The r squared cancels with the r squared. The k, the I sub 0, and the L cancel with the k, the I sub 0, and the L. The pi here cancels with one of the pi's, and this pi cancels with the other pi. The z sub 0's cancel, and what I'm left with is 4 times 1/2 times 1/16 divided by 1/12. And if you plug that into your calculator, you get 1.5. So the directivity of an infinitesimal dipole is 1.5. Now the directivity of an isotropic antenna, which is the same in all directions, is 1.0. That's the lowest directivity that you can have. So an infinitesimal dipole is just barely more than an isotropic antenna. It's not a highly directed antenna. It's very, very close to being isotropic. Now in practice, that equation is quite difficult to evaluate for anything more complex than what we just did. Even that was pretty complicated, but more typically, we're going to calculate the directivity in a different way. We're going to calculate the directivity from what's called the half-power beam width, which we'll abbreviate as the HPBW. The half-power beam width is the width of the beam for which the signal is at least half of its maximum power. You know, if I look down here at this figure, here is where the maximum power is, and then of course in the opposite direction as well. You could come down a certain distance and figure out, oh, this must be where it is a half of its value, and then the angle that is formed by those 2 points, that's the half-power beam width. Now, I should probably not have done that because I actually did it for real here. So here you can see this is S max, and whatever S max is, I can calculate 1/2 of S max on both sides, find the 2 points that correspond to S max over 2, and then find the angle between them, and it turns out in the case of the infinitesimal dipole antenna, it's 90 degrees. So the half-power beam width is equal to 90 degrees, which we will often write in radians, so it would be pi over 2 radians. And if you think about it, you know what? The narrower the half-power beam width is, the more directed the antenna is going to be. So if this were just like a laser beam, so if it were like this, then I would think that the half-power beam width would be extremely narrow, and the directivity would be very high. So in general, I would say that as the half-power beam width decreases, the directivity is going to increase. Now, mathematicians and physicists have actually found a relationship that's very detailed between the half-power beam width and the directivity. We're going to see that soon, but for right now, I just want to mention that we don't necessarily have to solve this problem graphically. Although I've solved it graphically here, you can also just plug in the actual numbers. So what I'm going to do is I'm going to calculate the normalized, so the normalized intensity is equal to the I of theta comma phi divided by I of theta comma phi max. So what this does is this allows us to account for the fact that that maximum value, this S max right here, might be something other than 1. You know, if it's 1,000 or if it's 0.01, we need to be able to divide that by a factor of 2. It turns out for the infinitesimal dipole, I'm going to skip a step here, but it's just sine squared theta. You know, if you scroll back up to the infinitesimal dipole, we saw that it is, we have the intensity, which is the average Poynting vector. The average Poynting vector is this quantity right here. Whoops, let's jump just as I was writing. The average Poynting vector is here, but this is the maximum of the average Poynting vector. If you take the ratio of those two, everything will cancel out except for the sine squared theta. So only the sine squared theta is going to stick around, and that sine squared theta is the only thing that's going to impact the half-power beamwidth and the directivity. So if I know that that represents the power, then I know that I need to say sine squared theta is equal to half. It's equal to 0.5 because I want the half power. I want the beam width at which it is half the power, and this equation right here is setting the power to half. So I'm going to say theta then is the inverse sine of the square root of 0.5. And this, of course, has an infinite number of solutions, but the first two are 45 degrees and 135 degrees. So if you look up here, you can see 45 degrees would be, you know, like right about there, and 135 degrees would be right about there. And if we were to say that's going to be the half-power beamwidth, then that is 90 degrees, because it's going to be the half-power beamwidth is going to be 135 degrees minus 45 degrees, which is 90 degrees. So I don't have to solve the half-power beamwidth graphically. If I can write the equation and figure out what is the normalized function, then set it equal to 0.5, solve for theta, then I can find out analytically, I can find out mathematically what the half-power beamwidth is. Now let's take special note of something. I'm going to really draw your attention to this because it's something that it will get people every time on the final exam. You have to take special care to note whether the polar plot or function that you're considering is a power plot, in other words, whether it's of the Poynting vector, or an amplitude plot, which is to say that it's the electric or the magnetic field. If it's a power plot, then you want to set it to 1/2 because you want 1/2 of the power. But if it's of just the electric field or the magnetic field, remember that the SAV is going to, I'm going to say it's going to vary as, so I guess I'll say it's proportional to E squared. So if we need to take this down by a factor of 2, then we need to take this down by a factor of the square root of 2. So that as E goes down by a factor of the square root of 2, then when it gets squared, it will take it down by a factor of 2. So if you're talking about an amplitude plot, then you go down to 0.707, which is 1 over the square root of 2. If you do it in decibels, it would be 3 decibels. So recall that the Poynting vector will square that term. 0.707 squared gives you the half power that you're looking for. And I will be very clear in the assignments and in the exams to say whether it is a polar plot of power or whether it's a polar plot of electric field or a magnetic field. So here we have a polar plot of electric field. So right away, as soon as I see that, I know that I'm looking for points that are 0.707. And I've chosen a particular finite dipole antenna where the length of the antenna is equal to the wavelength of the signal. And so you can just see right off the bat that this seems to be narrower than the plot was for the infinitesimal dipole. I'm going to solve it graphically, but I'll just mention to you that, of course, I generated this figure using MATLAB, so I actually have access to the numbers in MATLAB, and I can go in and I can see them precisely what they are. So, for example, I can tell you that this value right here is 1.2 times 10 to the minus 4th. So the maximum value of E is 1.2 times 10 to the minus 4th. I'll say 0.707 times the maximum value of E is equal to 8.48 times 10 to the minus 5th. I'm going to look where, and it's hard because this is a pretty broad range from 0.5 to 1 on those two rings. But if I look for the place where it's, about 0.85, it's going to be right about there, something like that, and then similarly, symmetrically, something like this. So this is going to be where it's 0.7 0.707 times the max. And then it's just a matter of figuring out what is the angle that corresponds to that, what is the angle that corresponds to that, and what is the angular difference. Now, if I were to look at this and try to eyeball it, I'd probably say, you know, it's probably in the neighborhood of about 110 degrees, maybe something like 110 degrees. And if I were to look over here, I'd probably say that that's something like 70 degrees. So I might have guessed that it would be a range of about 40 degrees. That's about as precise as I can get because, again, I don't have a finer mesh, a finer grid on this picture. What I can tell you is that when I actually look into the data, theta of the half power beam width is 66 degrees and 114 degrees, and therefore the half power beam width is equal to 114 minus 66, which is equal to 48 degrees. So you can see that I was actually off by about 25% in my estimate there, but it's the best that I could do given now that I look at it, you know, I could probably have said, well, that's probably about 100 and that's probably about 110. I probably should have guessed 115 and I probably should have guessed 75. Looking back at it now, I think I could have gotten a better estimate, but 48 degrees is the precisely correct answer based on the calculations that I did in MATLAB. Now, as I mentioned, there is a relationship between the half power beam width and the directivity of the antenna. It's an approximate relationship, and we're going to see that it can be off by a little bit, but it's going to be pretty good, and it's going to be really the main way that we're going to use to calculate the directivity of an antenna. Now, there are two angles in the denominator here. This first one is the angle that we've been dealing with. This is the half power beam width as we've sort of declared it. But I just want to remind you that if I come back up here, there's actually an antenna here, right? This is the finite dipole that's right here, and it has a radiation pattern going off on the side. And it's really hard. It's hard to see this. I don't even know if I can sketch it. But now I'm gonna look at it from a side view here. We've got the antenna is doing this, and it's also doing this, but it's also coming out of the page. So it's actually rotating around. It's like a donut with a hole that is not all the way through the middle. So it's basically like it's like a red blood cell. It's kind of smushed down in the middle, but it has a 360 degree radius in one direction. So in that direction, the half power beam width is just equal to 2 pi. So very often what we're going to find is that the half power beam width in the phi direction is equal to 2 pi. This is what we've been calling the half power beam width. And I should say that there are some examples. If you think about, like, if you had an antenna where it was like a cone or like a ray, well, then it would be very reasonable to assume that ray or cone was a ray or cone in 3 dimensions. So what we're going to find then is that phi sub half power is very often 360 degrees or 2 pi radians, or sometimes it's equal to the half power beam width. So only if you were really if you knew that the signal that was coming out of it was conical, that would be like the Yagi antenna. If you had a Yagi antenna, then you would probably make the assumption that the half power beam width in both directions was equal, because really there it's a cone. But if you had a finite dipole antenna, and it is really so hard to represent this graphically, but you have to picture that this image right here is being rotated out of the page, and it's being rotated 360 degrees. And in that case, then, you would choose phi sub half power to be 2 pi. And so anytime that you have a finite dipole, which is most of the time in this class, we're going to choose phi sub half power to be 2 pi. So what is the directivity of an infinitesimal dipole antenna? So we know that theta sub half power is equal to 90 degrees, which is equal to pi over 2. And we know that in this case, phi sub half power is equal to 2 pi, which is equal to 360 degrees. There is in the phi direction, nothing changes. It doesn't, if you're standing off in one direction of the finite dipole or in another direction, it doesn't matter. As long as you're not toward the ends, that's all that really matters. And so we can say that the directivity is approximately equal to 4 pi divided by pi over 2 times 2 pi. And if you work that out, you get 1.27. Now we know that this is less than the correct value, which is 1.50. We know that it's exactly 1.50. So when I say that it's approximately equal to 1.27, yeah, they're very close, fairly close. It's off by maybe 20%. And as the directivity gets to be higher, it's a better approximation. The infinitesimal dipole is kind of the worst case scenario here, but it's also the only one that I know the actual correct value of. So we wanted to do that comparison. Now let's use the directivity that we found in example 31.6 to find the. Let's take the half power beam width that we found from example 31.6 and calculate the directivity of that antenna. So we know that theta half power was equal to 48 degrees, and that's equal to 0.838 radians. And we know that phi sub half power is just going to be equal to 2 pi, which is 360 degrees. So the directivity is approximately equal to 4 pi divided by 0.838 times 2 pi. And that works out to be 2.39. So confirmed, the directivity of a finite dipole antenna with L equals lambda is higher than the directivity of an infinitesimal dipole. Even though these are both approximations, it is still, I think, reasonable to say that based on these results that they are, in fact, it is greater than for the infinitesimal. Let's talk about efficiency and gain. The efficiency of the antenna, eta, and this Greek letter eta is what we always use to represent efficiency, says if you deliver a certain amount of power to the input terminals of the antenna, a picture here is the antenna, and let me draw it as a proper dipole. So you got the power is coming in along a transmission line. We're going to be radiating power away from the antenna. It actually radiates in both directions, but I'll just show it like this. There's going to be some power that's coming in. I'm going to call that the input power. There's going to be some power that's being radiated away. I'm going to call that P-rad or P-rad. And what we find is that the efficiency is what fraction of the input power gets converted into radiation. We'd like that to be a very high number. Ideally, we'd like it to be 1. We'd like it to be 100%. In practice, it's more like 95%, 96%, something like that. Because, of course, the conductors are not perfect and the insulators are not perfect, so there can be some imperfections there. And so ordinarily, we don't deal with the imperfections very much, but in this one case, we're going to account for those imperfections with eta. So if we have a 95% efficient antenna and we're giving it 100 watts of power at the input, then 95 watts of power would be converted into electromagnetic radiation. That would be a pretty good antenna. And now we're going to take two things that we've already found, the efficiency and the directivity. We'd simply multiply them together to get the gain of the antenna. So the gain says, given a certain amount of power, how does this antenna convert that input power into radiated power that is directed in the direction that we care about? So if the efficiency goes up, the gain goes up. If the directivity goes up, the gain goes up. The efficiency can be any value between 0 and 1. The directivity can be any value greater than or equal to 1. So the gain can be any value from 0 to infinity. So if we have a dipole antenna that has a wavelength of 1 lambda, it converts 96% of its input power to electromagnetic radiation. What is the gain? Well, the gain is the efficiency multiplied by the directivity. We're told that the efficiency is 0.96, and we calculated in a previous example that the directivity of that particular length of an antenna is 2.39. Multiply those together, we get 2.29. So that's much easier than the things that we've been doing so far, but it's nice to know that we can combine this concept of efficiency and directivity. Okay, effective area. When you think of effective area, I want you to picture like you're trying to scoop up a whole bunch of water in a bucket. The bigger the bucket, the better, because you're going to be able to scoop up water faster. Let's imagine you're trying to catch butterflies. Well, the biggest butterfly net is going to be best because it's going to catch the most butterflies. In the same way, we can refer to an antenna as having an effective area. By the way, the alternate name for effective area is the aperture. So the aperture or the effective area of an antenna talks about how much of the signal can it catch. And so effectively what we're going to do is we're going to say you take however much power is available in the air, that's the S average, the average Poynting vector, you divide that into the power that's available at the terminals of the antenna. So now I'm going to draw the antenna coming the other direction, and I have signals that are coming into the antenna, and I want to know how much power is coming out of that antenna. So if a P sub L means power to the load, it's the load of the antenna. So I would be sending it to some sort of probably transistor amplifier. So the definition of the effective area is how much of the radiation, so how much of this S average gets converted into P sub L. Maybe it would be a lot, maybe it wouldn't be very much, but it's helpful to know what that quantity is. So the effective area can also be, and we aren't deriving this equation, I'm presenting this equation to you. I will tell you that it can be derived. It's lambda squared over 4 pi times the directivity if we assume that there are no losses in the antenna. But if we assume that there are some losses in the antenna, then that d is replaced by g. Remember that g is just equal to eta times d. So all we've really done here, going from 3118 to 3119, is we've added the concept of efficiency to that equation. So you could also then say, well, the effective area will increase as the directivity increases. So that's like saying if the antenna is very focused, and if it's pointing in the correct direction, then it will be able to grab more of the incoming signal. So maybe you would have an antenna that was really optimized to receive the signal in a particular direction. You know, if you think of like a satellite dish, the typical satellite dish like this is definitely optimized to receive signals that are coming in along the axis of the antenna. It will really receive those signals very well if they are parallel to the axis of the antenna. But if a signal is coming in this way, it's not going to receive it very well. So the effective area will be increased as the directivity of the antenna increases. So let's calculate the effective area of a finite dipole antenna with L equals lambda. We're going to assume that the lossless insulators and conductors, so eta is equal to 1. Whoops, that's M. Eta is equal to 1.0. The antenna is transmitting a signal at 10 megahertz. Well, the first thing I'm going to do is calculate lambda. Lambda equals C divided by F, which is 3 times 10 to the 8th, divided by 10 times 10 to the 6th, which is 30 meters. And then from there, it's actually a pretty easy calculation to find the effective area. It's equal to lambda squared over 4 pi, times d times the efficiency. Well, the efficiency is 1, so this is going to be 30 squared divided by 4 pi, and the directivity we found in the previous example was 2.39. So this works out to be 171 square meters. It's in units of square meters. Think of that as like how big is your catcher's mitt? How big is the bucket that you're using to catch these signals? The bigger, the better. The bigger, the more effective it's going to be at catching the signal. And then finally, we come to the Freeze transmission equation, which is going to bring everything together that we've been talking about. Ultimately, the only thing that matters, if you're talking about antennas, is I'm sending power into the transmitter. How much power comes out of the receiver? Ultimately, nothing else matters. Yes, there are efficiencies in the transmitting antenna, so you have to deal with the efficiency. As you're worrying about the direction that it's transmitting, you've got the directivity of the transmitter. You've got the directivity of the receiver. Those things, I guess this is efficiency of the transmitter and efficiency of the receiver. Those two combine together to form the gain of the transmitter. These two form the gain of the receiver, and then the gain of the transmitter can be used to calculate the effective area of the transmitter, and the effective area of the receiver comes from the gain of the receiver. But again, ultimately, all of that is math. Ultimately, the only thing that matters is going from the transmitted power to the received power. We really need to be able to calculate that ratio of P received divided by P transmitted. Do we receive 1%? Do we receive 10%? Do we receive 0.0001%? Actually, in some cases, 0.0001% would be okay. It would even be desirable. So we know that the radiated power of the transmitter is equal to the total power that comes from the transmitter multiplied by the gain of the transmitter. Remember that includes both efficiency and directivity. So we're going to assume that these two antennas are pointed at each other, that they're in an optimal orientation. There are, of course, more complicated equations that could deal with the angle between them, but we're not going to worry about that for right now. We're going to assume that they're pointed optimally at each other. So the total power, that total power that we just found right here, the radiated power, is spread out over a surface area of 4 pi r squared. So we can take P sub t times G sub t and divide it by 4 pi r squared, and that gives us the S average that is being received at the receiver. So that's S average right here. S average is what we just found in equation 31.21, the S average that's at the receiver. Notice, by the way, that it has a 1 over r squared, which makes me very happy, because usually these things do have a 1 over r squared relationship. Now, the power that is coming out of the receiver, let me come back up here. This power coming out of the receiver right here is, by definition, that is S average multiplied by the effective area of the receiver. So I can multiply those two together, and it gives me the power that's coming out of the receiver. Now, of course, what I'm going to do is I'm going to take this, and I'm going to plug it in for S average, and I get this quantity. Now, I can go way back up to the equation that was used to define the effective area as a function of gain. I'm going to solve that for the gain, and I'm going to apply it particularly at the transmitter. So I get a relationship between the gain at the transmitter and the effective area of the transmitter. We've been talking about effective area for receivers, but remember, we talked about complementarity. It's also sometimes called reciprocity. The reciprocal relationship, or the complementary relationship between a transmitter and a receiver, says that the effective area, if it's good for a receiver, it's also going to be good for a transmitter as well. So if we substitute that equation in for G sub t, so this all goes in for G sub t, we end up with equation 31.24. We're going to cancel the 4 pi's. We're going to move the lambda down into the denominator. We're going to move the P sub t over to the left-hand side, and we're going to move the A sub r up into the numerator, and we end up with the Friese expression, the Friese transmission equation. It simply says the effective area of the transmitter multiplied by the effective area of the receiver divided by lambda squared r squared. That's going to give you the relationship between the received power and the transmitted power, and that's the only thing that ultimately we really care about. So I guess I would have expected these two things in the numerator, and I would have expected the r squared in the denominator. I'm actually a little bit surprised by the lambda squared in the denominator. I wouldn't necessarily have expected that, but what it does tell us is that as lambda gets larger, this ratio on the right-hand side is going to get smaller, and so less and less of the signal gets through. That means that higher frequencies are going to be received more efficiently than lower frequencies. It's one of the reasons why there's a constant push to move things to higher and higher and higher frequencies, because it does, in fact, give you more efficiency in the transmitted and received power. Also notice the symmetry of this equation, that I don't really care which one is the transmitter and which one is the receiver. If antenna A transmits to antenna B or antenna B transmits to antenna A, this ratio is going to be exactly the same, because the A sub E comma T is multiplied by A sub E comma R. It doesn't matter what the order of that multiplication is, and the R distance between them is going to be the same in either case. So let's figure out. I have 100 watts going into at 10 megahertz, going into the input terminals of an antenna. It's a finite dipole with length equals lambda, and I receive the signal with an identical antenna that is 1 kilometer away. What is the output power of the antenna? We'll assume that both antennas are 95% efficient and that they're pointed directly toward each other, so they have maximum directivity. Okay, so we need to calculate A sub E comma T, which, by the way, because these antennas are exactly identical, it's also equal to A sub E comma R. This is equal to lambda squared over 4 pi times the gain, which is going to be 30 squared divided by 4 pi multiplied by the directivity, 2.39, multiplied by the efficiency, 0.95, and that's equal to 163 square meters. So now I can directly apply the Friese transmission equation. This is going to be A sub E comma T, which is going to be 163, times A sub E comma R, which is also 163 because the antennas are identical. They don't have to be identical, by the way. You can have one very good antenna, one very bad antenna. Divided by lambda squared, and lambda was 30, so this is 30 squared, and multiplied by r squared. 1 kilometer is 1,000 meters. So I get 2.95 times 10 to the minus fifth. So I'm getting about 3 times 10 to the minus fifth, like if you think of it as percent or portion of whatever's going into the transmitter is arriving at the receiver. It's a really, really, really small fraction. Let's see if it says that we're giving 100 watts to the transmitter. So P sub r is equal to 2.95 times 10 to the minus fifth times 100 watts, and therefore we're receiving 2.95 milliwatts at the receiver. So we're receiving a tiny fraction of the power that's going into the transmitter is being received at the receiver, but 2.95 milliwatts, that can make Wi-Fi work, that can make your cell phone conversations work, it can make any sort of wireless connection can be handled no problem with about 3 milliwatts. So, summary of today, we saw a lot of different quantities today. We talked about how to calculate the input impedance, which is also called the radiation resistance. So we calculated those quantities for both an infinitesimal dipole, which you have infinitesimal dipole right here, or my advice is look at figure 31.3 if you have a finite dipole. The directivity is the maximum signal intensity in any one direction divided by the average signal intensity in all the directions. The directivity of an isotropic antenna, which is the same in all directions, by definition is equal to 1, and the directivity of an infinitesimal dipole is 1.5. The half-power beamwidth is the angle over which the antenna is transmitting at least half of its maximum intensity, half of its maximum power. The half-power beamwidth for an infinitesimal dipole is 90 degrees, and it gets tighter than that for a finite dipole, something like 70, 60, 50 degrees, depending on how long that antenna is. The directivity of an antenna can be approximated by 4 pi divided by theta half power times phi half power. Theta half power is what we called the half power beamwidth, and phi half power is the half power beamwidth in the other direction. Typically, it's going to either be equal to 2 pi or it's going to be equal to theta sub half power. Efficiency measures how much power applied to the antenna is converted into radiation, and gain is the product of efficiency multiplied by directivity. The effective area measures how well does it convert incoming radiation into power that can be applied to a load. The effective area can be calculated as lambda squared over 4 pi times the gain. And then finally, the Freeze transmission equation is really what we care about. It talks about the transmission of power from end to end, from the input of the transmitter to the power that's coming out of the receiver.